my screen?
Yes, teacher. Also, I am learning this right now. Now in my assessments, now I'm going to have assessments next week. So this Newton's 3 laws of motion is coming. Like Newton's first law of motion is coming in my exam, in my
assessment. Okay. Yeah, I will just recap these 3 laws of motion of Newton's, and I will cover them in detail. I mean, not all of them, but I think the first and the second one we will discuss in my next class, which is on Monday for grade 6. Okay, but even for circular motion, you need to know these 3 laws of motion. It will help in the understanding of the circular motion. Okay, so let's get started. Okay, so Newton's 3 laws of motion. What is the first law? What is the first law? Yes.
Motion.
Okay, Zainab. Who is this Galaxy S8? Please kindly use your original name. Who is this? She's not connected to the audio. She cannot hear me. Oh, okay. Okay, Avara, would you like to tell me the first law of motion? Okay, Omar, go ahead.
Okay, yes, the first law of motion.
Okay, yes, Vara, yes.
Yes, the first law of motion is that if a body stays at rest, or if it's moving, it continues to move unless there's an external force which makes it behave in a different way.
Right. So in other words, you are defining inertia, right? Inertia is the resistance to motion, and by motion, I mean velocity. Velocity, which includes both speed as well as direction, right? So any change in velocity is resisted, and that resistance is called inertia.
Good, teacher.
Yes. Okay. So the first law of motion talks about inertia, which inertia is the resistance to change in motion. Motion includes both velocity as well, speed as well as direction. Okay. So it can be, if an object is moving, it will keep moving at the same velocity if no force is acting upon it. And when we say force, I mean to say net force. Okay, because there are a lot of forces acting on an object at any particular time, but we are talking about the net force. If all those forces have balanced each other out and the net force is 0, then that means there is no change in velocity. The velocity will stay the same. So if an object is at rest, it will stay at rest until a force acts upon it. If an object is moving, it will keep moving in the same velocity until an object changes its direction or maybe stops it. Okay, so that's how it is. I like to think about it as, we all have inertia. We all have inertia. It helps me in understanding. Like, when at night, you don't want to go to sleep. And that's why most of the people go to sleep very late at night, because they don't want to go, they want to do other stuff. Okay, so it's difficult to go to sleep. But once you sleep, it's difficult to get up, right? So that's like inertia. You can think of inertia as that way. So changing from one activity to another is difficult. That's inertia. Changing from one state to another, that's inertia. Okay. Then if you have any net force acting on an object, there will be acceleration in the same direction as the force. Okay? Remember, this is Newton's second law of motion, and is equally important that the direction of the net force will be the same as the direction of the acceleration that it will cause. And I want you to pay attention to the fact that I am talking about acceleration. I'm not talking about velocity. Velocity may or may not be in the direction of the force, but acceleration is always in the direction of the force. Okay, what did I mean by that? We will come to that later. Then third one is really easy. Every action has a reaction, right? Can you give me an example? of this third law of
Right,
motion.
teacher? What motion?
Yes,
Can I tell you?
yes,
Oh, teacher,
yes.
every action has a reaction. For example, if you are squeezing, then by squeezing something, its shape is changing or its size is changing. This is what they meant by that. Every action, meaning some force like squeezing, has a reaction changing the shape of something or size.
Okay, so what's the reaction in your squeezing example? So action is you squeezing. So what's the reaction? Shape change?
Yeah, shape changing, also the direction of movement.
Speak loudly.
Oh yeah, okay, teacher. That for that's in squeezing the size of an object changes, also the shape of an object changes, and and also the
You see, every action has a reaction, meaning that for every force that you apply, there is an equal and opposite force. Okay, this is what I mean. So if this is the action force, this is the reaction force. So when you are, for example, this is the can, and for example, this is the squeezed can because you exerted force, the reaction would be whatever is inside must have come out. It can be air, it can be liquid, it can be anything, whatever was inside. So that coming out was also exerting a force. And that, yeah, yes, speak loudly. Yes.
So if it's an empty can and air comes out, that's also a reaction.
Yes, yes. And also this can will be exerting an equal and opposite force on your hand. When you are squeezing the can, aren't you feeling? Don't you feel the sharp edges of the can? Don't you feel the force? Right? So that is the equal and opposite force, what your hand is feeling, and also the force which must be exerted by whatever is inside coming out. Okay, so every action has a reaction. For example, an easy example to understand that I use. Yes, Sidra? Yes.
If a car is going in the friction of the tire and the road, and the reaction is the air resistance.
Okay, so car is moving, and so yes, friction can be thought of as its reaction. Yes. Another very simple example that I use is when you slap on the wall. When you slap on the wall, do you feel that tingling sensation on your palm?
yes,
So consider, yeah, so consider that the slap from the wall on your hand. So, you know, when you exerted a force, an equal and opposite force was exerted by the wall on your palm. Okay, so when you slapped on the wall slapped back on your palm, on your hand. Okay, so that's a very easy example to understand. Okay, every action has a reaction. Okay, so equal and opposite force. So now we will use these three laws of motion in understanding the circular motion. How is circular motion different from linear motion? Yes, Zainab?
In linear motion, you're just traveling in one direction. It could be either backwards or it could be either forwards. But in circular motion, your direction is changing continuously. Like,
Very good.
once
Very
you're
good.
maybe traveling a bit straight, but then a force is acting, pulling you towards the middle. So then your direction changes every single second.
Very good. Yes, yes. So the one big difference between linear and circular motion is of direction. In a linear motion, an object just keeps traveling in one direction, right? So the direction doesn't change frequently. But in a circular motion, the direction is changing every single instant. Instant, what do I mean by instant? Split of a second, every moment. That's why we have circular motion. Okay, if this object keeps traveling in the same direction, even for a few instants, you will see that the motion will no longer be circular, but it will be distorted. Okay, why do we call it uniform circular motion? By uniform meaning that the magnitude of the velocity, or you can say the speed, you know, for my lecture, for my class, I will use the word speed for its magnitude and direction, to denote its direction. Okay, So when I say speed, understand that I'm talking about the magnitude of velocity. Remember, velocity is a vector quantity, and so it has two components to it, magnitude and direction. So speed meaning the magnitude, okay? So by uniform circular motion, what we mean to say is that the speed stays the same, meaning the magnitude of the velocity stays the same, but the direction keeps changing. Every single moment, it keeps changing, okay? And another unique thing about circular motion is that, which I found very confusing, and that's why circular motion is a little hard to understand. It's not common sense. It doesn't come, and by the way, leave the common sense behind in physics. Common sense just misleads you, and common sense is just an illusion, okay? So instead of helping you understand physics, it confuses you, okay? So leave the common sense behind for the moment when you're dealing with physics. That's why people find physics hard, because they try to use their common sense. The thing is, another thing which is unique about circular motion is that in linear motion, you must have observed that when, for example, this is a car, when a force is applied, the car moves in the same direction as the force. Oh, what happened? Sorry. So the car moves in the same direction as the force. So this is easy to understand, right? But in circular motion, that's not the case. In circular motion, the force is acting towards the center of the circle. Just assume that this is the center of the circle. Okay, my circle is not perfect. Okay, this is not the exact center, but just assume that this is the center of the circle. So the force is acting towards the center of the circle, but the velocity is exactly perpendicular to the force, unlike the linear motion, where the velocity was in the same direction as the force. So that's why I said, remember in Newton's laws of motion, when I wrote this equation, force is equal to ma, I said the force and the acceleration need to be in the same direction, but not necessarily the velocity. Force may or may not be in the same direction as the velocity. Like in this case, the direction of the force is the same as the velocity, but not in circular motion. In circular motion, that's not the case. The velocity is exactly perpendicular to the force. This is called the centripetal force. Centripetal meaning center seeking, meaning it is constantly trying to bring the object towards the center of the circle. Though it's not successful in doing that, but it is trying. And it is because of this trying that it is able to pull the object down in the shape of a circle, in a curved path. The reason why it is coming down is because the force is trying to bring it down, but because of inertia, because the velocity is so high that the ball is not getting enough time to fall to the circle, to the center of the circle. And so because of this force and because of inertia meaning it is resisting that change in direction. Inertia is the resistance to change the direction. So because of that inertia and the velocity is so much, it's not getting time. And so it is ending up in a circular pathway. So if the force is acting towards the center of the circle, then that means the acceleration also must be directed towards the center of the circle, because the acceleration and force, both of them are in the same direction. Okay. Remember, when you have vectors on both sides of the equation, they should be in the same direction. Otherwise, this equation is not valid, meaning they are not equal to each other. Okay, when you're dealing with vectors, okay, and they have to be in the same direction if they are part of the same equation. Okay. So we understand that velocity at any instant, for example, when it reached here, again, velocity is always at a tangent to the curve. What is a tangent?
radius of the circle?
Is that it?
I mean, that's what I know.
Okay, yes, Zainab. Yes, what's a tangent?
A tangent is a line which just touches a point, just one point only. And it is a line, in a tangent, we use it to find the gradient. Normally, at least that's what I know in math. And in math,
Okay.
it's with graphs, so the point of the tangent is equal to the point of that curve. Because at that specific moment, they both are at the same point. So if it wasn't in a curve, it would have traveled straight. But since it's in a curve, the value would be different. But at that specific point, the gradient of both the tangent and the curve would be the same at that point.
Yeah, you are correct about tangent, but only one point that I would like you to remember what Sidra told. So Sidra missed your point and you missed Sidra's point. So combine the two together and then you have a complete definition of what a tangent is. So yes, tangent is that line which is touching a circle at a particular point, but it is also perpendicular to the radius of that circle. Now, you might say that in math, we deal with graphs. We don't have circles, they are graphs. But yes, they are also curved. And as long as they are curved, they are part of a circle. They're part of a circle, okay? Every curve is a part of some circle. That circle must have its radius. So tangent is always perpendicular to that radius, okay? So velocity is always tangent to that circular pathway. So no matter at what position of the circle the object might be, the velocity is always at a tangent and is always perpendicular to the radius. So appreciate, I made these three positions. Okay, this is the mass and this is the radius. Okay, also denoting the centripetal force and acceleration. By the way, centripetal force as well as centripetal acceleration, both of them are directed towards the center of the earth. Sorry, not the earth, circle. A is for acceleration, C is for centripetal. Okay, now, since the direction of velocity is constantly changing, though the speed is the same, but the direction is changing. And as long as the direction is changing, that means the velocity is changing. And any change of velocity, be it in its magnitude or direction, is an acceleration, okay? And the direction of the acceleration will be the same as the direction of the force, which is causing that acceleration, which in a circular motion is towards the center of the circle. Okay, so is there any question so far? Is there any question so far? Okay. Okay, let's move on. I also want you to appreciate another fact. If I am applying a force in the same direction as the movement of the object, what will happen? The speed will increase, right? If a ball is already rolling and I further push it in the same direction, what will happen? It will fasten up, right? Speed will increase, but the direction will not change because the direction of the force was the same as the direction of the velocity. But if the ball is rolling in one direction and I apply the force in the opposite direction, then what happens? What happens? Yeah, do you think the ball's direction immediately changes and it starts rolling in the opposite direction? But no, it will take time. This is inertia. It will take time. First of all, it will slow down. Okay, eventually it might stop. It depends upon how much force you applied onto it. And then if your force was too much, then yes, you will change the direction. Like for example, in cricket, when the bowler throws the ball towards the bat, it's coming with a speed, but what does the batman do? He strikes it with enough force to make it go in the opposite direction. So not only did he decrease the speed, but he actually gave it a speed in the opposite direction. Okay, so that's a lot of force. Now, what happens when the force is exactly perpendicular to the velocity? When this happens, the thing is that the speed does not change. This is circular motion here. The speed does not change, but only direction changes. And the direction of the object changes towards the force. And so this is a mixture of inertia as well as the force. So there are two forces battling here with each other. One is inertia. Okay, it is, resisting the change. And this centripetal force is trying to bring it towards the center of the circle. And so the combined effect is that there is a curved path. There's a curved path or curved trajectory of the ball. Okay. 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 So what happens if the object's velocity is not too high? Sundas, you tell me. If the velocity of the object is slow, loudly. Yes. Did you guys hear? Did you guys hear what she said?
It was a bit.
I'm sorry, but I didn't hear that.
Yeah, so if the velocity is too small, if the velocity is too slow, the centripetal force will win, and there will be enough time for the to overcome inertia, and so the thing will fall towards the center. Okay, the thing will fall towards the center, so it will lose its circular motion. So if the velocity is too low, that's exactly what will happen. The centripetal force will win over, and it will fall. It will try to fall towards the center of the circle. And that's exactly what they are showing here on page 37, when they're trying to explain the pathway of a satellite. Okay, so what they're here in path B and C. Okay, can I zoom in? Yeah, okay. In path B and C, the velocity is not too high. Okay, so therefore the gravitational pull, which is the centripetal force in this case, is causing the object to fall towards the center of the pathway, right? Now here in case of D, it is moving with good velocity, with high enough velocity. And so yes, the inertia wins over. Okay, and so therefore it continues in its pathway round and round. Okay, and because these satellites are in vacuum, there is no air resistance. So due to inertia, it keeps orbiting, or it keeps revolving around the Earth. Okay, what happened? Yes.
I'm sorry.
Okay, let me just. Yes. Yes, go ahead.
About this circle. This circle, this one. So
okay.
Wouldn't then you say that force is equal to mass times by velocity over radius?
Yes, I'm coming to that. Yes.
Oh, okay.
Okay, are you Vara?
No, I'm Zaran.
Okay, which grade are you?
Grade 8.
Grade 8. Are you guys doing circular motion?
We finished it.
Oh, you finished it. Wow. Okay, so okay, tell me, if this centripetal force is removed, what happens and why? If the centripetal force is removed, then what happens?
A centripetal force is a force which keeps an object to move in orbit. So if the centripetal force is removed, then the object will no longer orbit around where it's supposed to be.
Okay, then if it doesn't orbit, what does it
goes off track.
Okay, then what does it do then? I mean, if it doesn't orbit around, what does it do? Does it fall towards the center of the circle, or does it go out of the circle of the
It will go out.
Out where? I mean, how will you mark its motion? Out?
It will go out, not in, because there'll be no force bringing it in.
No, no. Think about inertia. Think about inertia. So it was the centripetal force that was making sure that it goes in a circular pathway. Okay, so I will try my best to make a circle. Okay, so this centripetal force, when this is removed, now this object is here, right? And what was the direction of its velocity? It was this, right? Considering that this is absolutely perpendicular. So this was the velocity. It will continue following the first law of motion, inertia. When this force is removed, it will continue its motion, meaning a force is required to change that velocity, right? And constant change in velocity is what kept the circular motion. So if you remove the centripetal force, it will continue in the direction in which it was traveling, which was that. So the instant you remove the centripetal force, the object will continue with that instantaneous velocity in the same direction. So you will say that the object will fling out in the tangential direction, will fling out in a tangent. Do you understand that?
Yes, thank you.
So what did you understand? Can you repeat?
What's it called?
Can you repeat what happens to the object when you remove the centripetal force?
Sorry, my mic was muted. If the centripetal force is cancelled, then the object will sling out into its previous
Right.
in the way its tangent was.
Yes, yes. Like for example, can you focus this a little? Yeah, okay. Yeah, okay. For example, in this particular, if the string breaks at this point, the ball will continue in this direction, okay? And if the string breaks in this at this point, the ball will go in this direction, okay? So on and so forth. So that's exactly what will happen to the ball. They ask this question very frequently in MCQs and even otherwise. Okay, now let's come to your formula, the formula that you were asking about, that acceleration is equal to the square of velocity divided by the radius of the circle. Yeah, zoom out. I want both these circles. So anybody wants to discuss on why is it that acceleration is equal to the square of velocity divided by the radius of the circle? Any ideas? Yes, Sidra? Yes. Please loudly. Come here.
Because velocity is the rate of change of
Rate of change of displacement.
Displacement with time. So acceleration is the rate of change of velocity with time. So what velocity is rate of change of displacement with time. So
yes, you can use this. Yes, you can use this. Yes. Go ahead. Yeah, please be
okay.
fast.
So if we write the velocity, so velocity is displacement over time. So we are doing the rate of change of velocity with time for acceleration. So that means that this whole thing is getting the rate of change of, right?
Yes.
So this gets squared.
Okay.
And so you get this acceleration equals v2 over time.
No.
Yeah, because that.
No. Any ideas? I saw a few hands raised. Yes, on this. Yes, please hurry up. Okay.
So I think if you decrease the radius, if you decrease the size of the radius, the rate of change or displacement increases because the circle decreases.
Loudly.
Because the circle decreases in size. So at any given moment, it's changing the direction faster.
Okay. Anybody else? Yes. Yes, Zainab.
I think Miss that its acceleration is equal to velocity square over r, because if acceleration is over here velocity square, and velocity is the distance over time, and
Yes.
acceleration is the rate of change of velocity, and the radius is over there also, because if the radius increases or decreases, it will affect how much the acceleration of the object.
Yeah. Okay. So, okay. Let me, this, I don't know if this is included. I mean, this, I'm just, you should know why a formula is there. I mean, you should know the proving of the formula. You should know how that formula is derived, if you ask me. So I will do a real quick derivation. Khan Academy did it and I loved it. Okay. I can even forward the Khan Academy videos where he has done this in a very simple way. So let me just do it real quick. So this is a normal circular motion. Okay, this is the center of the circle, and this is the radius, and this is the velocity. The same diagram that I just explained to you. Okay, in the first page, this is the same diagram. But what we have done here is that we have made another circle, but like we have translated the vectors here. Okay, we have translated the vector. So you can say that this circle is an analogy circle. You know what an analogy is? When we use examples to understand, this is an analogy circle just for our understanding. Okay, this circle is only for our understanding. Okay, so what have you guys done translation in math? Translation of vectors?
Not in grade 8, Miss, at least not so
Yes.
far.
Okay. Yeah. Okay. So good. So I am translating the vectors. The vector here in this diagram is velocity, right? So I am translating this vector here. Okay. Here. So velocity is the radius of this circle. Velocity. And remember, when we represent vector in the form of an arrow, the size of the arrow depicts the magnitude, remember, and then the arrowhead depicts the direction, right? So, so I have translated this vector velocity 1 here, this velocity 2 here, velocity 3 here. So can you see that I have made sure that the directions stay the same, though I have translated them, but the direction stays the same. Can you see? And so because the magnitude of the velocity is constant, remember, the magnitude of the velocity stays constant in circular motion. So the radius is constant of this circle, okay? Just like velocity is the rate of change of the position, right? Velocity is the rate of change of position, or you can say the rate of change of displacement with time. In the same way here, acceleration is the rate of change of velocity, okay? Here, the rate of change of velocity is acceleration, okay? Now, why did I make this analogy circle is because I'm trying to prove this. I'm trying to prove this, okay? So now, if I translate the accelerations, now you might be asking that we just learned that acceleration is directed towards the center of the circle, but look at these accelerations, they are tangential. They are not pointing towards the center of the circle. So why is that? Now, these are instantaneous accelerations. Okay, if I translate this acceleration here, for example, this is acceleration 1 for V1. Now I am translating it. So give me that pink marker and I will translate it and I will say this is acceleration A here on this circle. If I have to translate acceleration here, A is here. Okay, then give me the blue marker and acceleration 2 for V2. Acceleration 2 for V2. is here. So can you see when I'm translating, the direction stays the same. Now V3 acceleration is this way, okay, this way. So let me use a black marker. This is acceleration 3. So can you see all the accelerations are pointing towards the center of the circle on the original circle. In the original circle, all the acceleration vectors are pointing towards the center of the circle, just what we learned, right? So don't get confused. Okay. Now, how do we find out the time taken for an object to complete one circle, to complete one whole circle? So we will make use of the formula which Sidra also spoke about, and which is velocity is distance divided by time, that Zainab also spoke about, right? Yeah, distance or displacement. Displacement divided by time. Okay, displacement divided by time. Okay. Now, if I want to find out the time for one complete circle, that is also called a period, which is denoted by a capital T. Period is time taken for one circle or one. Okay, so if I swap the places, time will be equal to displacement or distance, whatever you want to use, divided by velocity. Is that right? Right. Okay. Displacement in this particular case, displacement is what? What is the displacement here? It is, what is the distance traveled by the object in one complete circle? It is the circumference of this circle, right? So what is the formula for circumference of a circle?
2 pi r.
2 pi r, thank you very much. Yes, so 2 pi r, okay, I've done it here. 2 pi r, okay, divided by the velocity, right? So time is equal to 2 pi r divided by the velocity. Now using the second circle, okay, again, I want to calculate the time period taken to complete this whole circle, which will, by the way, these two time periods should be equal. They should be equal to each other. Why? Because it will take the same time, because they are denoting the same time period, okay? So here in this case, radius is velocity. So instead of radius, I have replaced it by v. I've replaced the r by v because in this case, the radius is v. And we have what is analogous to velocity here in this circle? A. What is analogous to velocity in this circle? It's a. So I have replaced it by a. Okay, now these two should be equal to each other. So if they are equal to each other, if they are equal to each other, 2 pi r over v is equal to 2 pi v over a, where a is the centripetal acceleration. 2 pi, because they are on both the sides, they get canceled, or you can say dividing both the sides by 2 pi, you will get rid of the 2 pi's. And what you're left behind with is radius multiplied by centripetal acceleration is equal to v square, because velocity gets multiplied by itself. If you rearrange it, you will have centripetal acceleration is equal to square of velocity divided by the radius. Okay, so this is the derivation of the formula. Now, using Newton's second law of motion, which states that an object accelerates there is an acceleration when there is a net force acting on it, and force and acceleration are in the same direction. So replacing acceleration's value from this equation, instead of acceleration, I wrote down this value. So centripetal force is equal to the product of mass square of velocity divided by the radius. Is everybody convinced with this equation now? To some extent, at least. Is there any question so far? If there is any question, please, you're most welcome. Yes? Okay.
So these values will be proportional?
Sorry?
Are these values proportional?
Yes, according to the formula, looking at the formula, I mean, it shows that there is proportionality going on in here, okay? So now, if you have understood this equation, if you're convinced, then remember I told you in my previous physics classes that whenever they ask you factors affecting something and that something has a formula, then look at the formula to find out the factors. So what factors are affecting the centripetal force? If anybody asks you, in the question or in the exam, what factors affect FC? Not that they will ask you such a straightforward question, they will ask you in a twisted manner. But if they ask you, what are the factors? So in order to, instead of ratifying and memorizing, if you know this formula, if you understand this is from Newton's second law of motion, MA, and you know that A is for circular motion square of velocity divided by R, just replace it. This equation should come to your mind. And if you have this equation in your mind, it's easy. Mass of the object, velocity of the object, and the radius of the circle. Okay, easy peasy. These are the three factors that affect the centripetal force. Okay, now of these factors, radius is the only one which is affecting it inversely. Do you understand? Because radius is on the other side of the fraction bar. The radius is on the other side of the fraction bar. So that means if radius increases, centripetal force should decrease. And if the radius decreases, centripetal force should increase. So they are going in the opposite direction. So if this increases, this should decrease. Okay. And if this decreases, this should increase. Okay. But on the other hand, velocity, can you see squaring of the velocity? Square of velocity. So if, for example, velocity was initially 2, so the square of 2 is 4. So the force must be 4 multiplied by something, whatever the mass is, divided by whatever the radius is. But if, for example, it increases to 3, it will affect the centripetal force by, look at, the mass will stay the same if the radius stays the same. Can you see from 4 to 9, there's a big increase from 4 to 9. Though the force increased, though the velocity increased by only 1 unit, the force increased by so much, 5. So that means velocity has a big impact on the centripetal force. It affects it acutely. Okay, and that is why I said that if the velocity of the object is not enough, what will happen? The centripetal force will immediately cause it to fall to the center of the circle. Okay, and then the radius of the, radius I already discussed. Okay, now if there is any question so far, please ask. Now remember, centripetal force in itself is not one particular type of force, but it is different in different situations. Okay, it is different in different situations. For example, what is the centripetal force when a car is bending a curve? Can anybody answer that? What is the centripetal force when a car is bending a curve? Come on, that's an easy question. If you guys have done it in school. Yes, Zainab?
Could it be the air resistance, miss?
No. Yes, loudly, Sudhus. No. No. Yeah, it's hard. You know what? It took me so much time to recap all of this and, to make sense. This is a difficult, why this is difficult is because it's hard to imagine.
Miss, what about friction?
Very good. Yes. So what friction? Friction between
the car and the road, or
the tires and the road. Yes.
Yeah.
Yes. Yes, very good. Yes. But another question that was bugging me since yesterday was that friction, what's the definition of friction? What's the definition of friction? Real quick.
It is like when two or more things are attracting to like moving, causing some species of like moving together.
Okay, who's this? Who's this, please? Wait, you're not using your original name, so I don't know your identity. I usually remove such participants, but so please kindly use your identity. Yes.
Yeah, it's the Muhammad Manib. Like I did also the before classes with you of biology. So yeah.
Okay. Okay, so Muhammad.
So friction like means that when like two surfaces are shedding each other with a force.
Okay. Yes. So
Ma'am, could I answer?
yes. Yes.
The resistance force between two objects?
Resisting the force between two objects. Is that
No,
what you said?
no, I'm saying that I said that the resistance force between two objects. Like when two objects are against each other, so there's a resistance force.
Yeah, basically in simple words, if we say resisting motion, okay, resisting motion, it is a force that resists motion, okay? So my question was that if friction is a force that resists motion, how in this case is it assisting in motion and it's a still frictional force? You know, this question was bugging me. Yes, Zainab?
Friction means that it stops a body from moving in a certain, like it's friction is opposing force of a moving body, and centripetal force is a force which pulls an object towards the center. So when an object is moving in a circle, it has speed. So it's the reason, it's the speed which is the reason why it's moving in a circle. And if there's friction, it'll slow the object down to a point where the centripetal force will like be able to pull it to the circle. So in this case, the friction represents the centripetal force.
Yeah, you know what? Remember, we did two types of friction, static friction and then dynamic or kinetic friction. Do you guys remember that? We did in first term. I don't know with which grade, but I did it. Do you guys remember? Does anybody know static friction and kinetic friction? Yes, Sidra? Yes. Who?
Kinetic friction. Kinetic friction?
Yes, dynamic or kinetic friction, and then the other one was a static friction. Yes, I did. Yes, I did.
Like static friction, like it is a friction like between two or more solid objects, like that are not moving relatively to each other, I guess.
Okay. And then kinetic. Yes, you are right. So remember, I did this, that when you have, for example, okay, let me use something. Okay, I'll use this. Okay, this is a pencil holder. Now I am
Okay, so like what about the kinetic friction? Like, is it am I right? Can you just explain me if I'm right that
but you never,
it is the force between moving surface?
yes, and static was not moving, right? Yes.
Yeah.
Yes, you are right. Yes, you are right. So it's okay. Okay, for example, I have this pencil holder, okay, and I am applying some force. Okay, now I am applying some force. It's very small, but it is there. Okay, but that force is not enough to make it move. Okay, for example, let's say if an ant comes here or a cockroach comes here and tries to push it, well, it won't succeed. Why? Because, you know, they don't, and I mean, the force is not enough. The force is too small, but there is force, but it's not doing the job. So then that means there is something in this object which is resisting that force, right? That something is a static friction. That something which is stopping it from moving is a static friction. Now, when my force exceeds a particular value, that's when this object starts moving. And when it starts moving, there is still some force which is opposing this movement, and that is kinetic friction. So yes, you are right. Static friction is between two objects which are in contact with each other, but there is no relative motion between the two. And kinetic friction is when there is relative motion between the two, and also that they are in contact with each other. Remember one thing. If you have a wheel or a ball which is rolling on a surface, when you have a ball which is rolling on a surface, can you see that the contact surface is only 1 point? The contact between the two surfaces is only 1 point, and that is the reason why the friction is so small and we are able to travel on wheels and tires. Just imagine if the wheels were square. Do you think we could travel? No, because there is so much contact between the two surfaces. There is lots and lots of friction. So much friction, we won't be able to travel on square-shaped wheels. And therefore, the circular wheel does the job because the contact is only 1 point. No matter how big the wheel is, the contact is only 1 point. And therefore, because the contact is so less, the friction is so less, meaning kinetic friction is so less. And also static friction is less. Do you understand? So remember, we don't have any kind, there is no kinetic friction. There is no kinetic friction between a wheel and a surface. There is only static friction. That's it. So it is that static friction that provides the centripetal acceleration. And remember, static friction does not affect, it does not resist motion. It only stops, it only keeps the thing in its place. Do you understand me? Like, for example, if there is ice with melted water, you will see that, you know, it will slide a little, even if you don't touch it. It will slide a little. Why? Because the static friction is so less. It is so less. So static friction is what keeps the thing in its place, which stops it from sliding and moving here and there. It keeps it stable at 1 point. That is a static friction. So it is that static friction, and that static friction has nothing to do with resisting motion. It is only responsible for keeping it stable at that position. Kinetic friction comes in when that thing starts moving. But if it's a wheel, then there is no kinetic friction. We're talking about a kinetic friction comes in when the contact surface is considerable, when there is a lot of contact surface between the two moving objects. Do you understand that? So therefore, in case of car bending a curve, there is no kinetic friction. We're talking about static friction, and it is the static friction which provides the centripetal force. Okay, now what about a car on a banked road? Banked road meaning that the road is not flat on the surface, but it is at an angle to the horizontal. Horizontal being the ground, okay? Now, this helps in providing the centripetal force. How? Any idea? You can take hint from my diagrams. What is the centripetal force in this particular case? Centripetal force, remember, will always be directed towards the circular path. So what is the centripetal force here? Sundus? Looking at the diagram, any hints? Any raised hands? Okay, let me do it quick because we are running out of time. Okay, now remember, what are the forces acting on this car? One is, number foremost is the weight, okay, with product of mass and gravity vertically down, okay? Then we have this normal force. What is this normal force, Sundus? What is this normal force? Loudly. Loudly, no, it's not centripetal. Normal force is, again, Newton's third law of motion. Newton's third, don't whisper, say it loudly, okay? A normal force is the reaction of this surface on the car. And it is, why is it called normal? Because it is always perpendicular to the surface. That's why it's called a normal force, okay? So because the car is exerting some force on this, therefore this surface is also exerting a force on the car. So Newton's third law of motion, so we have this normal. Okay, yes, frictional forces also must be playing role, but I told you no kinetic friction here, okay? They're only static friction. Static friction is what is keeping the tires stable on the ground, okay? Okay, so if you, now what I did, I drew this normal with this horizontal. So I removed the bank, okay, in design for our ease of understanding so that we can understand it better. So I removed the bank and I only drew the normal with the horizontal, only the normal with the horizontal. So we can see that this normal is not perpendicular to the horizontal, but it is at some angle we don't know, but some angle to the horizontal. So that means this force is diagonal. It's diagonal. Now, whenever we have diagonal force, whenever we have a force which is not exactly vertical or horizontal, but somewhere in between, then that means that vector has some horizontal component and some vertical component. We did this in vectors, if you remember, okay, in vector addition. So now if this is diagonal to the horizontal, that means it has some horizontal component and it has some vertical component. So it is this horizontal component of this normal force exerted by the surface on the car, which is providing the centripetal force. Okay, this is providing the centripetal force, the horizontal component of the normal force of the surface on the car. What about the vertical component of the normal force? What's happening to that? What's happening to that? What's happening to the vertical component of the normal? Yes, Sidra? Yes? Come on, use your common sense. I'm giving you hint.
It's going down.
Source se bolo beta. Change to weight? Yes, what did you say? Who was that? Beta, it is cancelled by the weight. Equal and opposite, right? So how do we know it's cancelled? Because the car is neither moving down nor moving up. If any of these forces were greater than the other, then the car should have moved in the direction of the net force, right? So because the car is neither moving down nor moving up, but it is staying at one level, okay, above the ground. So we know that these forces must be equal and opposite, and so they are canceling each other out. Okay, so they are canceling each other out. So it is only this centripetal force which is unbalanced net force, and therefore it is causing circular motion of the car. Okay, is that clear? Okay. Then what is the centripetal force when we are on a roller coaster, looping the loop? You can take hint from my diagram. Yes, Zainab? So I made 3 positions of a roller coaster, and this is a car, for example, car
Gravity?
or whatever, you know. Yes?
Gravity?
Okay, I will talk about position A, B, and C. So you will tell me what the centripetal force is at position A, B, and C. Okay, first let's say A. Let's start with, oh, you want to start from C? Okay. Okay, Sidra? Yes?
C is gravity.
Yes, weight, gravity, yes. Plus the normal exerted by the surface on the car. Okay, what about B? Zor se. Yeah, what is it? What is the centripetal force? I told you centripetal force is different in different situations. So we're discussing the different situation. So this is a situation. What is the centripetal force here in this case? Yes, Zainab? Yes, Zainab? Come on. Normal force, the force reaction of the surface on the car. Okay. Secondly, static friction, okay, which is keeping the wheels on the surface. Both of them, okay, are providing the centripetal force. What about this position A? This again is the normal force, okay? You know why I made two arrows is because I thought this is more perpendicular to the surface, and so I said only the vertical component of it, but it's okay, same thing, okay? Same thing, it is the upward force exerted by the surface on the car, so that will provide the centripetal force at this position. Okay, my question is, why don't people fall down here at the top of the loop? Why doesn't the car fall down from the top of the roof?
The car has to go really fast so that it doesn't fall.
It's because of their acceleration.
Acceleration is also directed towards the center of the circle. So, yeah, okay. Yeah, Sidra's answer was close. She said the car is too fast for it to fall. Yeah. What do you mean by too fast?
Means that before it
Yes, okay.
Before it can fall or before the force can act, it just like goes.
It, yeah, zooms away.
That's exactly what happens if you like try that trick out with the bottle cap open and you have to flip it around.
Right.
The water doesn't fall because you do it too really fast.
Yeah, so you're talking about inertia. This is inertia. What you're saying is inertia. Inertia is resisting that change. So what happens is that car does not get time to overcome inertia. Before it can overcome inertia, it zooms past. Do you understand? So again, the velocity is high. Do you understand? The velocity is too high, does not allow time to overcome inertia. So inertia keeps it moving. And so by the time, even if it gets time, it would have, bypassed this point and it would have reached here. Okay, and that's why if you revolve a bucket filled with water, but real fast, if you do it real fast, the water won't spill. And I can forward you the videos. If you have a glass filled with water and you spin it round real quick, the water won't come out. Again, this is due to inertia. This is due to inertia. And so recently they have made these loops. You know how? You know, it goes up and then they leave some space and then the loop comes down. And so it's so scary. But what they do is they give a lot of velocity. They, push the car or whatever, the roller coaster, with such great speeds. And so when it reaches here, it just, like sort of flies in the air and reaches this part. And it's really scary. But the latest.
But doesn't all the energy like get used like climbing up?
Yeah, so yeah, they have to increase the velocity. And yes, it's dangerous. So yeah, and it's very, very scary. Okay, what about the centripetal forces for satellites and planets? Remember, if this is the sun, okay, and this is the Earth, and it is revolving around the Earth. So again, this is a circular path. So what is the centripetal force? Yes, Zainab?
It's gravity, miss.
Very good. Yes, it's gravity. Okay, let's real quick do the end of chapter questions. If there are any questions, please go ahead and ask me. Yes, I know we are ahead. Yeah, I know we are late. Okay. Okay, let's discuss the questions real quick. They're easy. An apple is whirled round in a horizontal circle on the end of a string which is tied to the stalk. It is whirled faster and faster, and at a certain speed, the apple is torn from the stalk. Why?
Miss,
Yes. Yes.
can I answer?
Yes.
So, because with the set, I have the wait. I have the answer.
Yeah. No, don't read from the back. Use what we have learned today in the class. If
No,
it
no, I'm
is,
not reading from the back. It's my notes.
oh, okay.
I'm just trying to find it again. Okay, basically, the more, what's it called? More mass, more centripetal force is needed. So here the velocity was greater, and that's why it got torn away.
Yeah. So when they're saying whirling faster and faster, and at a certain speed, so that means that the velocity is increasing. And remember, I told you velocity has a great impact on the centripetal force, because each time you're increasing, it's getting squared, right? So centripetal force is increasing tremendously, so much so that a lot of tension on the stalk, and eventually the stalk breaks. So you're going to give reference of this equation. I would like it, I mean, as they would like it a lot if you write this equation and you say that because velocity is a very important factor affecting the centripetal force, as the speed increases, the centripetal force increases so much that the stalk eventually breaks away. Okay, next question. A car rounding a bend travels in an arc of a circle. What provides the centripetal force? This we already discussed. Yeah, who's going to answer? Okay, Sundash, now do you know? What provides the centripetal force when a car bends in an arc of a circle?
The friction between the tires and
Yes, the static friction. Yes, friction. Okay. Is a larger or a smaller centripetal force required if the car travels faster? So again, you will write this formula. Okay, so if the car travels faster, what happens to the centripetal force?
Miss, if a car travels fast,
Yes, yes.
centripetal force is needed.
Bigger, larger, right? Okay, if the bend is less curved, loudly, please. Less centripetal force. Okay, and explain why. Yes, you are correct. Yes. Why? Beta, take help of this equation. So what are we doing when the bend is less curved? What's happening to the radius? Increasing. When less curved, meaning bigger radius. Bigger radius, and so it's inversely proportional to the force, and therefore smaller centripetal force. Okay, because they're inversely proportional. Is everybody clear about that? For example, this is a circle, okay, and so this is the radius. If I have a less, now this is less bent. Can you see this is more bent? If you look at this part, this is more acutely bent. This is less bent. So that means this is a part of a bigger circle and therefore bigger radius. Did you understand? So less bend, bigger the radius. Less bend, bigger the radius. Okay. The car has more passengers. That means
Miss, a larger centripetal force is needed because there's more mass.
very good job. Right. Question number 3. Racing cars are fitted with tires called slicks, which have no tread pattern for dry tracks and with tread tires for wet tracks. Why? First of all, what are treads?
Miss, the treads are the linings inside the tire.
Right. For example, this is the surface of the tire, and you have these ridges on the tires, okay, like different shapes, okay, like this. And then you have these treads even at the sole of your joggers. Okay, at the sole of your joggers, if you have noticed. If you have not noticed, go and see them after the class. Okay, so these are the treads. So what's the function of these treads?
Miss, these are to provide friction.
Right, right. Static friction, that is. But yes, kinetic also. Okay, yes. Yes.
Because in dry track, you don't need that much friction because it's a dry track. But on a wet track, because it's slippery, you need friction. That's why they are treads.
Yeah, because when the surfaces are wet, that means there's film of moisture or water in between the surfaces, and water is very slippery and it has very less friction. I mean, negligible friction. Okay, ice, melting ice is the slipperiest most surface that you can ever get. Okay, so because there is no friction, there are chances of car skidding. So if there is no friction, there will be no static friction when the car is bending around a curve. And if there is no centripetal force, what will happen? What happens when there is no centripetal force? Tangential. The car will keep going in the tangential velocity, as I just showed you. And so that's called skidding of the car, and that can cause accidents, fatal accidents. Right. Okay. Question number 4 is easy. A satellite close to the Earth at a height of about 200 kilometers has an orbital speed of 8 kilometers per second. Taking the radius of the orbit as approximately equal to the Earth's radius of 6,400 kilometers, calculate the time it takes to make one orbit. So they have asked us to find out the time it will take. The timing it takes to make one orbit. That means time period. Okay, so we will use this formula. Okay, we will use this formula. And so just plug in the values. Okay, in the question, they asked us to take the radius of the orbit as approximately equal to the Earth's radius of 6,400 kilometers. So when the question has already asked you to do that, so just do it. Okay, 6,400 kilometers will be taken as the radius divided by the velocity. Velocity in the question is 8 kilometers per second. So your time will also, if you're using this unit and if you're using this value, your answer will also be in seconds. Okay, the unit of the answer will be the same as the units that you use in your working. So if you work this out, what is the answer?
5024 seconds, Miss.
Yes, 50. Yeah, something.
5024, Miss.
Okay, 5024 seconds. Okay, so this is rounded to the nearest 1,000 will be 5,000 seconds. Okay, so with that, we have come to the end of this chapter. Are there any confusions or any questions regarding this topic? This topic is really complicated. So are there any questions? Okay. Okay, then see you inshallah on Monday. We will be doing inertia, Newton's first law of motion on Monday, okay, for grade 6. Okay, assalamu alaikum.
Assalamu alaikum.
Allah Hafiz.